Now, the second way of multiplying two vectors is the so-called vector product. It's also called a cross product because of the way we show it. Okay. We will be defining the cross product only for R2 and R3, and so we will be needing some knowledge on determinants, which means that we have to say a few things about matrices. Okay. A matrix, the singular, A of size n by n is an array of nm numbers. Okay. Or denoted by okay, Aij. I will just skip that part, such that they are ordered by the following. Okay, you observe that the first index shows the row number. The second index shows the column number. I will comment on it. And finally, we end up with, we have here n rows okay. Here, this is the jth column. Okay. And this one is the ith row. Here, n and m need not be the same, okay? But if it is, then we call A square matrix. Well, moreover, if A I, that is the diagonal element, are all one for all I, okay, in a square matrix, and all others are 0, then this matrix is called the identity matrix. shown by In if its size is n by n. Okay, that is In is the matrix 1, 0, 0, etc., 0, 1, 0, and so on. Only these diagonal elements are 1, all the others are 0. It's an n by n square matrix. Okay, and we also define the 0 matrix where all entries are zeros. Well, we can add matrices of the same size. So matrices of the same size can be added and any matrix can be multiplied by a scalar like vectors all termwise. Okay. This is the definition of addition and termwise multiplication of matrices. Well, right, let me give you two direct examples here as an exercise, as a way of getting used to it. For example, I have a matrix A, say 1, 0, 1, 2, 5, minus 1, and I want to add it to another matrix, but it must be of the same size, say 2, 1, 0, and 5, 1, minus 1. Okay. I can add them term by term, so 1 plus 2 here, 0 plus 1 here, and so on. So this is 2 plus 5, 5 plus 1, and minus 1, minus 1. Okay. The sizes are all 2 by 3, 2 by 3. And okay, I can multiply a matrix, say 1, 1, 2, 1, 0, 5, directly as 3, 3, 6, 3, and 0, 50. 2 by 3, 2 by 3. So this is a direct calculation of this sort. Now, an interesting thing about matrices is their products. Okay, we can multiply matrices. First of all, to multiply two matrices, we need the sizes, in some sense, matching. That is, not the same necessarily, but the number of columns in the first one must be the same as the number of rows in the second one. And this will be a matrix C where, okay, we have the following setting. Of course, it will be n by n. Let me write down what these are. A, okay, I will take the ith row, okay, that would be AI1, AI2, up to AKN. Sorry, what happened? AIK. Okay. So there are K columns and N rows. And then I will take the jth column. Okay. That would be B, okay, 1J, B2J, up to B, which one? That should be KJ. I'm not interested in the others at this point because I want to demonstrate how to multiply two matrices. You will do the same for every row and column. At the end, this will be the C matrix where I have somewhere Cij. So this will be in the jth row and ith column. So what is Cij? It is the ith row dot product, okay, the jth column. Of course, of A, and this is of B, which happens to be, okay, just take the dot product, okay, AI1, B1J plus AI2, B2J, and you continue up to the kth one, AIK, BKJ. Okay. One can formulate these things in closed form and other things, but that's not the point. Clearly, this is why you need the case matching. Okay, so basically, for every entry in the product, for every entry of the product, you should multiply a certain row, ith row, with the jth column. This is not as complicated as it looks. We will see it from the examples immediately. Okay, let us take, okay, say 2, 1, and 3, minus 1 as a matrix. It's 2 by 2. Okay. Now, the other one must have 2. Sorry, it must have, let me take it this way. It must have 2 rows, so say 0, 1, and 3, 2, okay? But it can have more columns. Okay. At the end, okay, we will have a 2 by 3 matrix, just like this one. Okay. So then, for the first term, which is C11, you take the first row and the first column, you take the dot product, which of course is 3. 2 times 0, 1 times 3. For the next term, you take this one and take the dot product with 1, 2. So that's 2 plus 2, that's 4. And finally, for this one, 2 times minus 1, which is minus 2. Do the same thing for the second row. 3 times 0 minus 1 times 3 is minus 3. And this is 3 minus 2, so it's 1. And this is minus 3, that's all. So it's this. Okay. A second example will show us some peculiarities of matrices. Okay. Let me consider for any A, okay, let A be the 2 by 2 matrix, which is A, 1 minus A, 1 plus A, and minus A. Okay. Now consider the matrix A square, which is A times A, which is A, 1 plus A, 1 minus A, minus A, multiplied by itself. Then, of course, this will be a 2 by 2 matrix at the end. We have the first row, first column, that's A squared plus 1 minus A squared, which is 1. We have, okay, A times 1 minus A, 1 minus A times minus A, the dot product, so it will be 0. We have 1 plus A times A plus A, okay, just 1 plus A times A, and this is minus A times 1 plus A, so that's 0 again. Finally, okay, this one times this one, that comes here. So that would be 1 minus A squared plus A squared, which is 1. So this is the identity matrix. It plays the role of 1 in general mathematical structure. Okay. So A squared is 1, roughly, but A is not I or minus A. So it doesn't look like real numbers in this sense. A still more peculiar example is the following. For all A different from 0, let B be the matrix BA minus B squared over A and minus B. Okay, B is any number, so just B is an R. Okay. Now consider B squared, which is BA minus B squared over A and minus B. You multiply by BA minus B squared over A and minus B. Well, this becomes, okay, BA, so B squared plus this product, which is minus B squared, so it is 0. This one, okay, BA minus AB, it is 0. This one, okay, minus B cubed over A, and this is plus B cubed over A, so that is 0. And the last one, likewise, is 0. So that's a 0 matrix, not just matrix. Okay. But, of course, B is not 0. So this shows that in matrix product, we have many, many peculiarities. For example, it's immediate from the first example, even, that if you change places, okay, you may have impossibility of multiplication, or you can have a completely different size. So in matrix multiplication, you are not allowed to change orders in the multiplication. Okay. Well, this much introduction would be sufficient for matrices. Now, matrices are structures where you have lots of numbers. These play an important role in solving a system of equations which do not contain squares of the unknowns and so on. So in that sense, they are linear equations. Just multiplication by a scalar and addition are allowed. There they play an important role. But we have some way of measuring, okay, matrices. That is not quite correct expression, but nevertheless, okay. We have the so-called determinants. Now, determinants, that simply means a value attached to a square matrix. So, for any square matrix, we can define a determinant of it. Now, these again play an important role in linear algebra. So those who will take 260 will, learn about these things quite a lot. But for our purpose, it's enough to define determinants only for 2 by 2 and 3 by 3. So we will define determinants of 2 by 2, 3 by 3, and of course 1 by 1 matrices only. Okay. For higher dimensional matrices, one needs the so-called cofactor expansion type definitions. And we will not do that here. So what's the definition? Well, the determinant of a number, or if you want, determinant of a 1, 1, okay, will be simply the number itself. This is our definition. For the determinant of a 2 by 2 matrix, now I did not write it here, not to confuse it with the absolute value. It's just the number itself, not the absolute value. But normally, we show determinants of higher sizes, okay, with a bar. Okay. This is not, of course, absolute value, okay, or norm. They can be negative, as we will see quite soon. So the definition, okay, is carried out by multiplying the diagonal elements. So what you do, you multiply these diagonal elements, and you multiply these diagonal elements, and you take the difference. So that is A11, A22 minus A12, A21. Now the same argument works for a matrix which is 3 by 3, say A11, A12, A13, A21, A22, A23, A31, A32, A33. Now, unlike this case, okay, if we consider the diagonals, we have only 2 of them. Actually, that's not exactly true. We can extend it a little bit. So add, starting with the first row, repeat these elements just for the purpose of calculating the determinant. And then let us construct the products of the diagonals. This is the first diagonal, this is the second one, and this is the third one. So that is, of course, as in here, we multiply the elements. So that would be A11, A22, A33, plus A21, A32, A13, plus A31, A12, A23. And then from this, we subtract, okay, the products of the other diagonals, which, of course, is this one, and then this one, and then this one. So that is, okay, A31, A22, A13, plus A11, A32, A23, and A21, A12, A33. Okay. This is the definition of the determinant of a 3 by 3 matrix. Now, of course, you should not memorize any of these things, only learn the method. That is quite easy, actually, once you get used to it. Let us see some examples. Okay, just calculation examples. Okay, the determinant of 1, 2, minus 1, 3, okay, would be, now that's easy, 3 times 1, minus 2 times minus 1, okay, so that's 5. For this one, it's a 3 by 3 case, 1, 1, 0, 0, 0, 2, and minus 1, 2, 3. Okay. Now here, we extend it a little bit, 1, 1, 0, 0, 0, 2. Okay. Now, the first diagonal is clearly 0. The second diagonal is 0. The third diagonal is minus 2. Okay. On the other hand, this diagonal is 0. This one is 4. Okay. And the last one, that is this one, is again 0. So it is minus 6. Okay. Now, this tells us that if we have a lot of zeros in the matrix, calculation will be easy. Because if you multiply something with 0, you get 0. Now, of course, we cannot change the places just like that in a matrix. The matrix will be a different one. But there are a few rules about determinants which say that if you change certain things, the value of the determinant will not change, or it will change in a certain way. These rules, called the elementary operations, to be more precise, elementary row operations, but it can be done for columns as well. Say the following. Firstly, okay, if two rows are changed with each other. So if two rows or columns, okay, in a matrix, in a square matrix, of course, are interchanged, then the value of the determinant is multiplied by -1. So if you change the places of two rows with each other 2 times, nothing changes. Okay. Secondly, if a row, of course term-wisely, or a column is multiplied by a scalar, lambda, then the value of the determinant is multiplied by this scalar. So just one row or column multiplies the value of the determinant by that constant. Well, the third property is the most important and the most useful one. If a row is multiplied by a constant and added to another row, of course, all term-wisely, then the value of the determinant does not change. Okay, this is the most useful one, so we will make use of that in a few examples. So, okay, consider the determinant of 1, 0, 0, okay, 0, 0, 1, and 0, 1, 0. Now, this is clearly something which very much looks like the identity matrix, but it's not. So, change the places. Okay. If we interchange these two things, then we multiply the value with -1. But we get I3, and its determinant is 1, so this is -1. So it makes the job a little bit simpler. Now the second example is better in this sense. Consider, okay, 2, 2, minus 2, and minus 1, 1, 3, and 0, minus 1, 1. And let us look at determinant of this matrix. Now there's only one 0 in here. Okay. Now, okay, if we take the third row, multiply it with 2, and then add it to the first row. Now, what will that change? Well, when you multiply this row with by 2, you will get minus 2. Add it will give you 0. So this term will give you 2. Add it here, it will give you 0. So we will get extra zeros. Well, which is a good thing in calculating determinants. And from the properties, nothing changed. So this is equal to the determinant of, now let us carry out 2 times 0 plus 2. Okay. And 2 times minus 1, okay, plus 2. And 2 times 1, okay, plus minus 2. And the others did not change. Okay. Now this determinant has the same value as this one. Okay. So let us calculate its value. Well, this is 2, and then we have 0 and 0, and then minus 1, 1, and 3, and 0, minus 1, 1. Okay. Recall, we add these two rows. Okay. Then, in this determinant, we have this product, which is 2, and then we have 0, and then we have 0. Minus the other products of the diagonal elements. So the first one is 0. This one is minus 6. And the last one is 0. Okay. So that's 2 plus 6. That's it. So these properties simplify calculation for us. Now, knowing a few things about determinants, now we can define the cross product of two vectors. This is valid only in R3 or R2, as we will see in a minute. Okay. We define the cross product or the vector product to be the determinant of I, j, k vectors times v1, v2, v3 here, and w1, w2, w3 here. Okay, this is the determinant. Now, this is not a determinant in the usual way. Okay, but the rules are the same. So here, okay, when we, for example, multiply the elements in this diagonal, we are not multiplying numbers, but we multiply two numbers with a vector, which, of course, v2 times v3 times the vector I. So the outcome is always a vector. because in every diagonal you have one of I, j, or k. Okay, so in this determinant, okay, calculation is the same as with scalars, but okay, at the end we get vectors. Now it will be better understood in some examples. Okay. Well, before I continue with direct examples, let me have some comments. Firstly, the outcome is a vector, as I already stated here. Okay? So it's called a vector product as well. Secondly, if we have two vectors, in R2, okay, we can think of them as vectors in R3 by putting an extra 0 at the end. Okay? Put 0 as the third component, okay, then they are in R3. And their cross product is defined. Okay. Secondly, the order is important. Namely, V cross W, okay, is a determinant. So, okay, if we change the order, namely W cross V, then the determinant will be multiplied by -1. Because if you look at the definition of the cross product, okay, we first write ijk's in the determinant. Secondly, we write the components of the first vector, and then the second vector. But from here to here, we are changing the places of the second and the third rows. Okay. So this has okay, a negative of the determinant, or this is equal to, let me say, V cross W. Since second and third rows are interchanged. So the order will be important. Well, over addition and scalar multiplication, one has the expected identities, namely lambda times V cross W. Well, this is obvious from the definitions. This would be lambda V cross W, or V cross lambda W. So you can put your lambda anywhere you want. You can take it outside, and so on. you can take the cross product of a sum and you can distribute it over the other. In the cross product way. And of course, any v cross 0 is obviously the 0 vector. This follows directly from the definition again, but you can check it just like that. And of course, this is just as important as these, but it's more important than these properties because we will be using it over and over again. Okay. Namely, if W is a multiple of V, that is, if they are parallel, then their cross product is 0. Hence, in particular, V cross V is always 0. Okay, we will generalize these things a little bit. Okay, now a very important property which can be directly verified from the definition of the cross product is the following. Okay? V cross W is a vector, all right. It is perpendicular to V and it is perpendicular to the W vector. So the cross product gives us a vector which is perpendicular to both of the original vectors. Well, this can be verified directly and very easily. By considering V cross W dot V is equal to the 0 value all the time. And similarly, this is the same as V cross W dot W. This is independent of the values of V or W. It's always so. Okay, and it can be verified directly. Well, let us look at a fifth property by considering an example. Okay, one can verify easily the following. I cross J is K. J cross K is I. And K cross I is J again. Now, of course, if you consider, for example, I cross K, that would be minus J. Okay? Because you change the order. Now let us consider I cross J cross J. Okay? And compare it with I cross J cross J. That is, I shift the parentheses to the other side. Now, because the cross product gives us a vector, I can continue my cross product with another vector, certainly, and so on. Now, here, this is the 0 vector, as commented above. So this side is the 0 vector. But here, I cross J is K. And K cross J is the negative of this, so it is minus I. So we see that they are not equal. So order, that is the place of the parentheses, is important. Okay? So unlike standard products, okay, parentheses, the places of parentheses are important. You cannot just shift them like that.